All right, we're going to begin our study of the properties and attributes of functions by talking about domain and range. This isn't brand new information for you. This is stuff that we've talked about as we talked about previous parent functions. We've usually had something to say about the domain and range of those functions. So this is partly a reminder, partly maybe a new way of looking at some things. So the basics of this are that the domain is just a way of communicating to people what the usable inputs are for a function. Typically, we start by assuming that everything is a possible input. And then we look for things that might restrict some of that input. And those restrictions come in a couple of different ways. One of them is an algebraic restriction. So, for example, we just got done studying exponential and logarithmic functions. If we had a function that looked like y equals log base 3 of x, okay, well, we know that we cannot take the logarithm of 0 or a negative number. So we would have to say that I'm not free to put any value of x in there that I want. The only values of x that I can put in there when I'm describing the domain here are x values that are greater than 0. Okay, it can't be 0, 0 had a problem, and it can't be a negative number, it can only be numbers that are bigger than 0. So one way to communicate this domain, there's different kinds of representations that we can use for that, is just like I did here, which is an inequality where I say the values that work, the inputs that work, are the ones that are bigger than 0. We also have what we call interval notation. In interval notation, that would look like this. We do an open parentheses, which says that 0 is a boundary point, but I can't use 0 itself. But I can use any number bigger than that, so I can go all the way to infinity. So I can communicate the domain of log base 3 of x this way as well. Okay? And that's consistent with what we put in for the parent function. Okay? There's some other parent functions that we haven't studied yet, but basically the algebraic restrictions that you would be familiar with at this point would be this one. So if we have a logarithm, so what we're not allowed to do is take a log of a number that is less than or equal to 0. Okay? So we're not allowed to do that. I'll kind of present these in the negative. We can not, so no division by 0. Okay, we'll do an example of one of those here, but we've known for a long time we're not allowed to divide by 0, so if an x shows up in a place that I put a number in would cause me to divide by 0, then I'm not allowed to use that value as an input. Okay, and the other one that you're probably familiar with is no square root of negatives. Okay. So we can't take square roots of negative numbers. These are the primary ones that we're going to have to worry about. There may be other ones that creep up as we get deeper into math, but for now these are kind of the algebra 2 level ones that we can run into. So we said we're going to do an example, another example. If I looked at the function y equals 3 over x minus 5, well, the fraction bar in there indicates that there is division is a part of this, and if I notice, if I were to put a 5 in for that x, okay, then I would get 3 over 5 minus 5, that'd be 3 divided by 0, so I'm not allowed to use that. Any other number I put in for the x, when I subtract by 5, I would subtract 5 from it, I'm not going to end up with a 0, so any other number should be fine. And so my domain on this one way to communicate that would be to say that x cannot be equal to 5. Okay, that is an inequality. It's not equals, it's not equals. So I could communicate it as an inequality like that. If I was going in my interval notation, there's a little bit more going on. I'll put that down here. I can use any number as far to the left on the x-axis as I possibly could go, which I symbolize with a negative infinity and open parentheses. And I can come all the way into 5 as a boundary, but I can't use 5. And then I can pick up at 5 again with the open parentheses because I can't actually use it, and go all the way out to positive infinity, and I put a union symbol in between these, a U without a little tail on that. In WAMAP, it's capital U is what you use in there for that symbol. Okay. I'd also point out that in WAMAP, if you haven't come across it, if you put negative lowercase o, it interprets that as being infinity, the two lowercase o's next to each other. So I won't do an example necessarily of the square root one here, but this is an example of a place where the mathematics itself creates a restriction that prevents us from using every possible number as an input. Okay. Practical restrictions come out of a story. The mathematics, when we model something mathematically with a symbolic equation, the natural assumption of the symbolic equation is every number is in play. Okay? But once we attach a story, some of those numbers don't make any sense. So when we look at this one, supercar's value after t months is modeled by 750,000 times 0.98 to the t. Okay, well, that's nice. Some values of t, if I'm looking at t as my input here, well, for one thing, it doesn't make any sense to start with a negative number. Okay? So a negative number off to the left there doesn't make any sense. If the supercar wasn't worth more before it was brand new, okay, $750,000 apparently was the starting price. We're familiar with that in exponential equations. Okay. But where does this go to? Can this go to infinity? We know that the exponential equation is allowed to use any possible input, so that's allowed to go to infinity. But this probably doesn't make a lot of sense after a certain point. Okay? A supercar after 200 years, okay, that this model probably doesn't work anymore. Now, can I nail down exactly when this model stops working? Probably not. Maybe I let it run for 10 or 15 years, if 10 years might seem reasonable on this, and somebody might tell me that as part of this problem, this will model the value of the car for the first 10 years, so that would be 120 months, and I could say this is what that domain looks like. Okay? As an inequality, that would look like 0 less than or equal to t less than or equal to 120. Okay? Because after 10 years, either this thing is falling apart now because it's been driven hard, or it's starting to cross over that line into being a classic. 1960s Ferrari probably goes up in value with each passing year. So this depreciation wouldn't apply to that after a certain amount of time. Okay. So that's an example kind of a practical place where a restriction of the domain because of the nature of the problem might be necessary. Okay. Range is just the outputs that you get from the usable inputs. Okay. So when we look at our restrictions on there, some of this range is a little bit harder to find out sometimes. Sometimes we can see it exactly. Okay. So every once in a while, when we have an equation that we know something about the parent function, we can get an exact range. If we know, for example, f of x equals x squared plus 2. Well, we know this is a parabola that's been shifted up to, its domain is all the possible real numbers, but the range, we know the vertex now is at 0, 2, so the range on this one would be the numbers from 0 to infinity. Okay? And this is talking about the outputs. This is y value stuff. Okay? Sometimes the best we can do is kind of approximate it. Okay? And or get what we would call a reasonable range, kind of like we had a reasonable domain here for our supercar. Okay? There may be some progression, for example, in the way that the fastball of a young pitcher progresses. Okay? And maybe it has to do with the length of some tendon in the arm is related to how fast somebody can actually throw a pitch. Well, there's a restriction, there's something about how long that tendon could possibly be. It probably can't be 0, and there's probably a maximum length in there somewhere, but it's not totally clearly defined in there. And in terms of trying to attach that to the speed of the fastball, well, there's other restrictions on there that at some point you're just not going to throw the ball faster. We've never seen a 125-mile-an-hour fastball, and that's far enough beyond the fastball that we have seen to say that, you know, the range on speed of a fastball probably has an upper limit. Okay? And there's probably a lower limit too, that if you don't throw the ball fast enough, you're never going to get it to home plate, so it doesn't really count. So there's kind of a domain or a range that is fairly loose in there. Okay, so oftentimes on range, we rely on pictures. And so if we look at this visually here, the domain, if we're looking at that, these little arrows that are on the bottom of this indicate this goes on forever in that particular direction. We recognize this as a parabola. There's no story attached to it. So if we're talking about the domain here, that is all real numbers. We can represent that this way with a symbol that says all real numbers, or as interval notation, it's negative infinity to infinity. Okay? The range on this one, we can see that it has a highest point. This is actually 4 up here marked on that axis, and so we can say that the only y values that we're going to get out of here, all our y's have to be less than or equal to 4. Okay? Or in the interval notation, that is all the numbers from negative infinity up to 4 and including 4. So the range, we're looking up and down this way, and we can kind of sandwich this in. If we had a horizontal line up here, we get to a point where that corresponds to the highest any point on this graph is, but on the bottom end, it just goes and goes and goes, and we're never going to be able to trap on the bottom side of it. So here's a kind of unusual looking function. I'm going to highlight a couple of things here. This dot is a solid dot. This is an open circle. We maybe remember that from number line things. And so if we try to do this same thing with domain and range, okay, our domain is about the x-axis, so that's, you know, when I pass a vertical line across here, what inputs actually have some output associated with them. Well, that is actually -4 back there. Okay. So the first number in my domain that makes any sense is a -4 that doesn't appear to be anything to the left of that for whatever reason. All of these inputs in here have corresponding outputs. So my vertical line is moving along the input axis, the x-axis here, and then I come out here, this is +4, and there's an open circle out there, so that means +4 is a boundary, but I can't actually include it. Okay, and then there's nothing out here. So that's my domain, and if I'm going to do the range, again, I need a line that is going to move along to, see if I can select that and make it more horizontal. All right. So up here, there are no outputs. This horizontal line that's moving up and down the y-axis, representing different y values, is intersecting nothing up here, but it does catch this point right there. So that looks like on the upper end for my range. I can get up to a 2, but no higher. And if I move this thing, if I can get a hold of it without moving everything else in the world, and move this thing down here, I see that there is a point where I can get all of these other values in between there. Some of them I can get a couple of different times. But then I get down to a point here where there are no outputs. Here, that's -2, and this does appear to have, because it has an open circle there, get those back where they were, that -2 is the boundary for the smallest number that I can get, but I can't actually get the -2, so my range would look like that in interval notation. Okay, as inequalities here, this would be -4 less than or equal to x, the equal to because of the square bracket, and I can actually get the -4, but just less than 4 because I can't actually get the 4. My other way to write the range here as an inequality, similar, -2 less than or equal to, or no, -2 just less than x, because I can't actually get the -2, less than or equal to +2 because I can get that one. Let's look at one more. This video is probably getting a little bit on the long side, so we'll try to wrap this up. My vertical line, again, let's do our domain check. That's close enough. I'm not going to force it to be. So if I start out here to the left, this one actually was intended to have an arrow going off that direction. We recognize that as, you know, a kind of horizontal asymptote behavior. Looks like it's going on there. We can't see exactly where it goes, but probably heading towards 0, probably that in behavior out that direction is a horizontal asymptote. So I come in here and I've got everything. Let's keep track of our domain as we're going along here. I'm coming in from -infinity, and I come in here and something happens in this gap between -1 and 0. I can, according to that solid dot in there, I can come in all the way to 1, that's fine, but then there's like some empty space until I get to an x of 0. And I can get that 0, and then I have these inputs, 0, 0.5, 1.5, out to 2 as a boundary, but not actually 2, and then nothing until I hit 3, and 3 is just kind of there by itself. So just that number, and then I join up those parts. Okay. So this would be, in inequality notation, I'd have to use a lot of ors. I could say the x's that are less than 1, okay, or between less than or equal to 1, between 0 and 2, or x equals 3. So as an inequality, that's how I would have to define my domain there. Okay. The range, let's take a look at the range. We need a horizontal line. Okay. We'll start at the low end. We managed to pick up this value at -1. But it's kind of there by itself. Okay. And we get nothing, nothing, nothing until this 0 across here. And as soon as we cross above that, we're going to catch that way out there somewhere. So I can't actually get the 0, but I can start at the 0, and this would go all the way up to here. And even though it kind of leaves on the left-hand side, it catches it on the right-hand side. So I can get a 1, and I don't need to break that up in my description of the range. I can go all the way to the 2, but then nothing more. So from 0 to the 2, and I can get the 2, and so I could join those things together and say that is my range. Or if I was describing it as an inequality, I would have to say x is equal to -1, or 0 is less than x is less than or equal to 2. I could describe it that way as well. Okay. So there's just more information on domain and range. It's going to be important concepts as we talk about some of the properties and attributes of functions in this unit.